managed to prove the necessary and sufficient condition to belong to a Morey class in one dimension. So we suppose that U is in LP lambda if and only if is held at continuous this function integral in x0 x of U with exponent p. So, thanks to this last theorem, we can show an example of P summable but not belonging to no one Morey class of the following function. So we use that necessary and sufficient condition to prove that a function is in LP but in no one LP lambda class. Precisely, let us define Ux as 1 over the fraction 1 over the absolute value of x, the logarithmic of the absolute value of x with exponent 2 or with the exponent 1 over p. This for every x such that the absolute value is between 0, so we of course exclude 0, and 1 over 2. And the exponent p is more or equals 1. This function in here belongs to LP in the ball centered in 0 with radius 1 over 2. But this function here is not in no one Morey class LP lambda b1 over 2, 0, for every lambda between 0 and 1. This fact is true using the necessary and sufficient condition, because let us consider not the function u but the integral in x0x of the absolute values of u with exponent p. This integral here is nothing else than 1 over the absolute value of the logarithmic of the value of x. This is not an Helder function with no one exponent, for no one exponent lambda, and then we obtain exactly what we promised, that we have a function u that is not in a one Morey class. So it's not obvious that a function, because of is in LP, is in some Morey class. So we consider with this example some kind of possible inclusions or not. As a remark, we consider the following function ui of xi defined in the interval ai bi with values in R. This function ui is in L1 lambda I for every I between 1 and n. Then, if these assumptions are true, we have that ux considered as the product of n functions that are u1 x1, u2 x2, and the last one un xn is in a Morey class L1 lambda, where in the product of the interval a1 b1, a2 b2 times, here probably it's better to put dots, an bn. Okay, so this function here is in L1 lambda. Lambda is the sum of lambda 1 plus lambda 2 plus dots the last lambda, that is lambda n. Therefore, using the previous characterization, is possible to build an example of function in Morey class LP lambda in the case of more variables. Well, Similarly, of what we have done before in the case of Lebesgue spaces LP, it's easily possible to define an analog of weak space. Let us consider precisely the weak class in a minute. We say that a function f is in the weak Morley class LP omega here if is through the following inequality, completely different from the LP lambda. LP weight is as follows: is less or equal to a constant with exponent with rho with exponent lambda, the following quantity: the supremum if t is more than 0 of t with exponent p times the measure of the following set of x in omega cap bx rho x0 rho such that the absolute value of f is more than t. So the set of x such that this quantity is more than t. This measure times t with exponent p. Okay? So, if this inequality is satisfied, f is in the weak Morley space. Okay? When, I don't know if or you recall the space as weak Lebesgue without the constant rho with exponent lambda. This is the weak Morley class. The quantity here, the constant in the second member, is independent of rho and x0. What is the relation between the weak Morley space and the Morley class? And the inclusion between one and the other. We will study these relations. The inclusions between Morley class LP spaces to vary of P and lambda, and in particular between NP and LP lambda, are obtained making use of Helder spaces and some inequalities. Also, considering a new class that we will soon define, we can have another variant of the Morley class. That is the following one. We define, let us consider mu a measure of bounded variation in the set omega contained or equals to Rn. So, we say that mu belongs to the Morley class LP lambda m, measure m, if is fired the following quantity: the supremum of x in omega, rho more than 0, 1 over rho lambda, and up to this is exactly similar to this one, but it's not the function f, it's the absolute value of the mu. This is the Morley class for the measure mu. So we will see in literature also this kind of class, where the integral here denotes as usually the total variation of mu in the set omega cap bx rho. These spaces here with the measure take the light of the same properties of the corresponding classical Morley spaces. So we will not talk a lot of this kind of classes because they have the same properties of the classical Morley ones. Well, now we will define another class, another variant of the Morley class that could be useful because we can remove the negative properties of the Morley class, that is the distance between f in the Morley class and L infinity is more than 0. Thanks to this variant of the Morley classes. Let us consider if we recall the previous remark here, consider if you recall the negative properties of the Morley classes, that is impossible to approximate in the sense of the Morley class LP lambda the norm of a function f. So this fact, these negative properties, raises the problem of finding possible subspaces of the Morley class LP lambda where this property could be true. For this reason, we can see this VLP lambda space. We will not use this subclass in the sequel, but their relevance for applications of partial differential equation is clear, because if we have that is removed the approximation of LP lambda with L infinity, so if we remove that the distance is more than 0, we can apply a lot of results that are in the classical study of partial differential equation in the Morley case. So the usage is this to remove the negative property. But now we need to start a result, and then we define this new class VLP lambda. Let us consider f in the Morley class LP lambda, where p is between 1 and infinity, and lambda is between 0 and the dimension of n. For h in Rn, we extend f with 0 out of the set omega. So let us consider a new function f, that is fhx, equals to fx minus h. Well, let us consider these functions fh. Then we have two facts that we will prove in this theorem. The first one is that if is equals to 0, the limit, if h tends to 0, of the Morley norm LP lambda of the difference fh minus f, then exists a sequence of function in C10 convergence to f in LP lambda. This is the first fact we will prove. Second one, if exists a sequence of function of C10 convergent to f in LP lambda norm, then the limit, if h tends to 0, of the Morley norm in LP lambda of the difference fh minus f is equals to 0. So let us start with the condition, the first one. Just to recall who is fh, fhx is f considered in x minus h. Well, let us set phi, a function in C10, such that is between 0 and 1, and such that the integral in Rn of this function phi x is equals to 1. Also, we suppose that the support of phi is contained in a sphere centered in the origin with radius 1. Well, let us also set phi j equals to the product of j with the exponent n times phi calculated in jx. So, fixed x0 in omega and rho more than 0, and consider f equals to 0 out of the set omega, we have to calculate the following integral. The integral in bx0 rho of the difference between the convolution of f and phi j x, all calculated in x, all this convolution, less than fx, all with exponent p, and the integral with exponent 1 over p. So what we have is that this is by definition of convolution is equals to the integral in bx0 is copied. Then we consider here the equivalent definition of convolution. So we have the absolute value is copied, the integral of f calculated x minus y phi j y dy in the set where y is between minus 1 over j, 1 over j. And then we copy minus fx the exponent p dx. All, of course, with the exponent 1 over p. Well, now let us just modify this quantity. We can consider that equivalently to this line, we can write the integral, the exponent 1 over p is the same, the integral in bx rho, the absolute value, and we can consider the difference fx minus y minus fx all multiplied by phi j. Now we can try to majorize this quantity here. Up to now we have exactly an equivalence. This is less or equal to, let us consider change of variables. So we put the integral calculated in the set where y absolute value is less or equal 1 over j. So changing the variable, we have phi y here, dy out. What is inside is the integral of the difference fx minus y minus fx with the exponent p, okay, then calculated in bx0 rho. So let us majorize again this quantity here. Now we have that if we multiply and divide here before this integral for rho with exponent lambda, we have one row with exponent lambda considered with this integral in such a way we can have the Morley class. Of course, we have here the multiplication by row with exponent lambda, and because of we remember that is all with exponent 1 over p, we have here less or equal row with exponent lambda over p, and then the other parts that are. So row with exponent lambda over p is the beginning. Then we can have the Morley norm of the difference fy minus f. But this is out of the integral, so we put the supremum where capital, where the absolute value of y is less or equal 1 over j. And what remains here is only the integral in the set where the absolute value of y is less or equal 1 over j, and inside the integral only phi j y dy. Then this is 1, so we have primum of the more class P lambda, or in the more space P lambda of the difference Fy minus F in the set where absolute value of y is less or equal 1 over j. What have we obtained? If we remember the first member here, we started from this convolution here. And we now obtained then that taking the limit for j tends to infinity, we have exactly the conclusion. So we have proved the first part I, this one exactly. If this quantity tends to 0, we have that exists a sequence of functions in C10 convergence to F. So we found the sequence of functions. The sequence of functions is the functions of fh, okay? This one, f convolution phi j x, calculating x, f convolution phi j. Well, let us consider now to prove the second part. That is, if exists a sequence of functions in C10 convergent to f in the more class P lambda, we have that this condition of limit is equal, is true. So let us now suppose that exists the sequence. Okay? So to prove double E, we have that exists. So here exists epsilon more than 0 and g in C10 such that this Morley norm is less than epsilon. Okay, so we now suppose that we have g. Okay, well, it follows that let us consider the integral in bx0 rho of the difference fy minus f, where who is fy? Fy is f calculated in x minus y. So now directly in the next lines I add and subtract the same quantity but g in x minus y and add and subtract gx. Precisely we consider less or equal a generic constant that is dependent on c of, let us directly allows me to write the following two lines. The integral in bx0 rho of the absolute value of f in x minus 1 minus g in x minus 1 minus plus g with exponent in x minus y minus gx plus gx. So here from these two terms we have add and subtract gx minus y, add and subtract gx. Okay, so we use the triangular property and we obtain three integrals. Okay, 1, 2, and 3. Let us remember what we have as assumption. Let us considering the assumption that we have this. So what we can majorize is the last term here. Okay? Also we have to reckon that g is in C0 in C10, and then we can majorize these three terms as follows. The first one is less or equal to the norm of f minus g in p lambda. exponent lambda. The same trick. We arrive from here to Morley, considering here 1 over rho with exponent lambda, and we obtain the Morley norm times rho with exponent lambda. Okay, we copy rho with exponent lambda. Well, second one is exactly the same quantity, so the integral in Vx0 rho of absolute value of gx minus y minus gx with exponent p, plus the last term is similar to the first, because we have the norm in Morley class LP lambda of g minus f, but once again, because we need here 1 over rho with exponent lambda, we have here the product with rho with exponent lambda. Well, now we have rho with exponent lambda only in the first and the third term. Now we use the uniform continuity of G, because G is in C1, 0. So, using the uniform continuity of G in Rn, we have that we can find delta more than 0, such that the integral in Bx0 rho of gx minus y minus gx with exponent p is less or equal epsilon rho lambda for absolute value of y less than delta. The application of the assumption of the uniform continuity of the function g. So here we force to have once again the quantity rho with exponent lambda. So now we majorize this term here with 3 quantities that have rho with exponent lambda, and we have almost finished, because we have 1 over rho with exponent lambda in the first member. We copy the integral in Bx0 rho of fy minus f with exponent t less or equal epsilon, because of we have the 3 terms that can be majorized with epsilon times rho with exponent lambda. What we obtained from this last inequality is exactly that the property number 2 is satisfied. If we want to go again in the statement of the theorem, we have proved that exists a sequence of functions in C10 class convergent to f in LP lambda norm, such that this quantity is equal to 0. So we now use this theorem. Precisely what we have now is that the above result allows us to assert that the closure of C10 in the LP lambda norm coincides with the set of functions of LP lambda for which the translation is continuous. We can now give the definition of the subspace of LP lambda that we were interested, because we announced before that we would like to remove the negative property of the Morley class, that is positive the distance between a function in the Morley class and L infinity. So let us now define the new class VLP lambda. Let us consider f a function in LP lambda. Okay? Now we set eta r. For a moment do not consider p. Eta r, the supremum if x is in omega and rho is between 0 and r of 1 over rho with exponent lambda, the integral in omega bx rho of the absolute value of f with exponent p. with exponent 1 over p. Or look here, we consider eta with exponent p as the norm with exponent p. Okay? Let us consider this quantity. We call eta r the modulus of Morrey of the function related to the function f, associated to the function f. So, considering this quantity eta r, let us say that v is in Vl p lambda if this quantity tends to 0 as the radius of the ball. The letter V means vanishing. This is the vanishing Morrey class. Why is vanishing? Because it tends to 0. This quantity tends to 0. Okay, so in the classical Morrey space, we have here rho between 0 and the diameter. If you see here, is fixed as the diameter. Okay, let us put here r. And if r tends to 0, this range collapses. Okay, if this quantity tends to 0 as the radius of the ball, f is in V LP lambda, or equivalent we say that is in the vanishing Morrey space P lambda. Okay? Instead, if f is in LP, the quantity that we consider as the modulus of absolute continuity of the function f with exponent p is omega sigma equals to the supremum if a generic set E contained in omega with measure less or equal sigma of the integral in E of the absolute value of f with exponent p or in 1 over t. Okay, so this is the modulus of absolute continuity. Well, let us consider f in the vanishing Morrey space LP lambda, in VLP lambda. Then we have that the limit if y tends to 0 of fy minus f in the norm of LP lambda is equals to 0. So, let epsilon more than 0 and fix omega the diameter, delta the diameter of omega. Let us also consider r bar such that r bar is between 0 and delta and is chosen such that eta in r bar is less than epsilon. Well, what we have is, we have to prove that this quantity is equal to 0. So let us start considering this norm. So the norm of fy minus f in LP lambda with exponent p is, by the definition, equals to the supremum if x is in omega and rho is between 0 and, recall here, the diameter of omega. Delta is the diameter of omega, 1 over rho with exponent lambda, the integral in omega per px rho of f t minus y, t is an auxiliary variable because we have used also y here, f t minus y minus ft, all the absolute value with exponent t. This is up to now the definition of this Morrey class. Well, this is less or equal. The supremum is considered in x in omega and rho between 0 and r bar. So 1 over rho with exponent lambda, the integral in omega of bx rho of f t minus y minus ft. Plus, adding and subtracting, we have the supremum in r bar delta. So we share all the set 0 delta. Okay? Rho originally is between 0 and delta. Now we consider the supremum in 0 r bar plus the supremum where rho is in r bar delta, or the same quantity. So we copied the integrand function exactly the same. Well, what what we obtain here is that we can majorize this quantity with the first one, if you remember, is eta r bar, this. So we consider eta r bar plus, we copied the supremum x rho is in r bar delta 1 over rho with exponent lambda, the integral in omega of the absolute value of ft minus y minus ft, or with exponent p dt. Well, what we have now is that this quantity could be also majorized considering here not rho with exponent lambda, but r bar with exponent lambda here. So we consider, copy the first term, eta r bar is the same plus 1 over r bar with exponent lambda. The integral is in all the set omega because we have previously majorized omega cap bx rho, so here we have not rho. Rho is only in the fraction before the integral. So we can remove the supremum here. 1 over r bar with exponent lambda, then the integral in all the set omega of the absolute value of ft minus y minus ft with exponent p. Then we are almost arrived to the conclusion because the thesis follows from the continuity of the translation function of the function f in LP. Now we are in LP because this is a constant. So we are not in the Morley class, but we are in LP, and in LP we can apply the continuity of the function fy or translation function. Okay? Then, in conclusion, what we obtained is that VL, the vanishing Morley class P lambda, is the closure of C10 in the LP lambda norm. This is true because, just a brief sketch of the proof. In the last theorem, we proved that if V is in the vanishing Morley class LP lambda, then the translation is continuous in LP lambda norm. And then, from the first part of the previous theorem, we obtained that f is in the closure of C10 omega. Second part, vice versa, we have that if f is in the closure of C10 omega, we have, by this definition, that for every epsilon more than 0 exists G in C10 omega, such that the norm in LP lambda of f minus G is less or equal a quantity that I choose epsilon over 2 with exponent p. I choose this quantity here, not only epsilon. Well, if this fact is true, we have for rho between 0 and r that is less than the diameter of omega, that 1 over rho with exponent lambda of f with exponent p in the set omega cap bx rho, that this is less or equal. I skipped some calculations, but we have that this is less or equal 2 with exponent p of f minus g in the LP lambda norm with exponent p plus 1 over rho lambda integral in omega cap bx rho of g with exponent p. Well, this sum of quantities is majorized as follows. The following one is less than epsilon. if we consider G as defined before, could be put over the integral. So we consider the maximum of G. What remain here inside the integral is only the function 1. So we have rho n as a majorization of all the integral, but we have also 1 over rho with exponent lambda, so totally we have rho with exponent n minus lambda. So rho is less than r. We can majorize this considering epsilon as before, the constant maximum of G as before, and r with exponent n minus lambda. Here, what we consider that if r is sufficiently small, we cannot consider this quantity here, and we can consider approximately that eta r is less than 2 epsilon plus another epsilon. So the proof is ended. Then, as a consequence of this fact, we have what follows as a corollary, that if V is in the vanishing Morley class LP lambda and epsilon is more than 0, then exists two functions f1 and f2 such that every function f in the vanishing Morley space can be considered as a sum of a bounded function f2 in infinity plus a function such that the Morley class, the Morley norm P lambda is less than epsilon. This fact is useful in the applications because before we prove this, I put in evidence that this fact to consider every function, not in Morley class, but for instance here we consider this in V lambda, VLP lambda, the vanishing Morley space. This can be shared in two functions, f1 and f2.
So VLP is always greater for 1 than 1, right?
Yes.
Do you have any results in 0, 1? Or I don't know. Morley spaces for 0, 1 in V?
F, let us consider F not in LP lambda, in VLP lambda. For every P more than 1.
But if it is in 0, 1, do you have something or there is some theory?
Yes, but the Morley space is considered also discontinuous function. So is if it's continuous, is easier the case. We can consider that is in LP lambda or in VLP lambda, not in C01. But we share F in two functions, one bounded, one in the Morley class. So here put not F but F plus F1, F1 plus F2. One is bounded in LP, and you can use this bounded condition very easily. The other one is in LP lambda, and this is a method that we will use to estimate the qualities of the solution, to consider not F but F1 plus F2. So this kind of corollary help in a lot of papers. You can share F in this way. So let us now prove this corollary. Here we have that VL is the closure of VL is the closure of C10. Because we have this, for every epsilon more than 0, is it possible to found G in C10 contained in an infinity such that this Morley norm P lambda of F minus G is less than epsilon. finish the proof because f is trivially considered as f minus g plus g. The part in parentheses f minus g is f1 and the second one is the f2 function. Then we have obtained that is true that f can be shared in these two functions, and this is repeated as a method in several papers when we like to obtain the Morley estimates of the solutions. Let us now like to make the comparison with other functional spaces. If we have not time to, of course, to finish, but just to announce, because we will continue in the next lesson. Let us illustrate some inclusions relation between Morley spaces and other spaces that are known in literature. The first comparison, very simple but necessary, is with the space LP, the level space. It's immediate from the definition that a function f in LP lambda is in the correspondent level space, so P should be the same. This is, of course, the first. The theorems below show the relationships between LP and LP lambda spaces. So, what is the relation between two Morley spaces? Let us suppose that we have LP lambda and LQ mu for different quantities. So, what we have is that we can prove that LQ mu is contained in LP lambda if P is less than Q and from here lambda is more. So we have this sort of balance. So let us consider P between 1 and Q, or if you prefer, P and Q both between 1 and infinite. Here it is allowed to consider L infinity also. So P less than Q, less or equal Q. Of course, if is equals is trivial. So let us consider P less than Q, and the quantity lambda and mi satisfy this inequality. Lambda minus n over P is less or equal mu minus n over P over Q. Then we have this inequality. Let us consider as a particular case this one. Let us consider u in a P more than n over 2. Here is a new condition, P more than n over 2. Then u, the function u is in L1 lambda if lambda is between n minus 2 n. So, look, if is in P, is in another Morley class, not P lambda, in 1, so you go down respect to P and arrive to 1, but you grow up with the exponent lambda. If you like, you can consider this as P0. So you go down with the exponent P, with the level exponent, and go up to the Morley exponent lambda. This is immediately C if we use Hölder inequality, because let us consider the assumption is that u is in LP, but we use later. Let us start for what from the thesis. U is in L1 lambda, so we have the integral of u with exponent 1 in omega gal bx rho. This is less or equal using Hölder inequality. So considering 1 times u, we have u with exponent p 1 over p. Here we have to add p, and rho because if we have the integral of the function 1, that under calculation is rho with exponent n times 1 minus 1 over p. So from this we have, of course here it's an exponent p. In such a way this is less or equal the norm of u in a p, and we copy rho with exponent n times 1 minus 1 over p. We obtain LP in all omega because we majorize omega cap b x rho with all the set omega. And then we have the norm of u in omega, in LP omega. Then this is true for every rho more than 0, x in omega. Then what we have, that this is the more exponent n, and what we obtain that is that u is in L1 n and 1 lambda. Who is lambda? Lambda is exactly n times 1 minus 1 over p. And because of p is more than n over 2, we have that n times 1 minus 1 over p is more than n over 2. So this quantity is less than n, and so this part is satisfied, and more than n over 2, because here we use the assumption p more than n over 2. Moreover, is immediate to prove, taking into account the absolute continuity of the integral function of the absolute value of u in p, that u is in L1 lambda. So we end the proof. Well, I don't know if it's time, but tomorrow we continue exactly from here. Thank you very much for everything, for you and for everybody.
Thank you. I think maybe not tomorrow, but on Thursday.
No, okay, of course.
Yes, but just remark. But okay, yes. So, any questions maybe?
Does the last keyword work also for n equals 1 and 2? Because then the range for lambda goes into negative.
You refer to this property?
Because if you take n equals 1 or 2, then lambda goes, well, n equals 1, this goes to the negative for lambda.
No. The lambda could be negative, but you, as we announced before, is not an interesting case.
Yeah, that's what I'm asking. So does the theorem doesn't state it true for n equals 1?
True for, sorry?
N equals 1.
N equals 1?
Yeah, is it true?
No, we consider that this is more than 1. No, R is...
Yeah, so that's
okay.
on the blackboard I didn't see on the slides, that's why.
No. This is from now on. N is more or equal to, should be more than 1.
If you balance in these spaces, if there are balances in these spaces, the articulate matrix system.
But yes, probably, but we are not interested in this. We studied the properties that we use for PDEs, so yes, probably it is.
Last question.
Yeah, the thing that you said, if there is some result for a p, but p c to 1, I mean in this range, because you are always using 1 infinity, but I don't know whether maybe someone is not interested
No interested, exactly.
in c to 1.
Yes.
Why?
P, for the exponent P, you say. But because we consider the summability historically, we repeat the theory of regularity for the label set LPP more than one, and because of a lot of properties are true only in that case. So we are interested only to consider P more than one, because we, in such a way, we obtain the results that are true in LPP more than one, and try to envelop that kind of theory. It's another kind of theory. In general, the summability is interested in that sense, P more than one.
Do you consider also more Rioli spaces?
Yes. There are a lot of variants of these spaces. In the next lesson, we will see Stummel spaces, Cato, class, other kind of spaces that are close to this, and the relation between the more one.
Yes. Are these spaces used to study some particular equation?
No particular, not a lot. Really, a lot of equations could be used. In literature, there are a lot of papers that consider this kind of class. Just we considered in 91, it was a paper by Chiarenza, Pasca and Longo, published in Ricerche di Matematica, 91, where the authors considered this class in LP and proved that U, Xi, Xj is in LP second derivatives. In 93, the same authors considered not only the interior case, but in Journal of Functional Analysis studied the global regularity. This is the interior regularity. And here they extend from local to global. After this paper here, started a sort of competition of a lot of authors to consider, similar to these two papers, this function here in the vanishing mean oscillation class, and this not in LP but in LP lambda. So Chiarenza, Pasca and Longo opened the way to new kind of studies of regularities, because they consider the VMO as LP. After that, the same equation with LP lambda was studies in interior case, in global case. After that, the divergence equation with the same assumption, the parabolic equation, so ut minus this with the same assumption, and also later the systems. So if you asked me for some good references where the story starts, I suggest you firstly this paper and this one. Because in these papers they express, they write, so firstly, this one, the representation formula of the second derivative. So they wrote not the second derivative less or equal something, but exactly equals to some kind of integral. So if we estimate these integrals, we have obtained the estimate of the second derivatives. If we have the equivalence of second derivative with operators, is natural to try to obtain the estimate of these operators. So in this case, they have the representation formula of the second derivative in interior case, and here they explain complete the representation formula in the case up to the boundary. These are probably the best references on all this theory. Okay. Thank you.
promised cake break, which is then the kitchen turned out to be quite small for everybody. So then the plan is to have it we have a bigger office of PhD students. So maybe the plan is to I think the cakes have arrived. So let's follow point.
Yes.
To